Okay, we're going to talk about some sample problems from section 4.6. 4.6 is where we wrap up chapter 4, where we're trying to figure out why we're using logarithms, some of the applications of it, and we get some really good ones when we get to section 4.6. So I hope that helps you kind of feel like you're doing something that has a purpose, learning some rules for a reason. One of the applications is in investments. So we have the base formula, and we've been seeing that for a while in the chapter, that A equals P. We have the E to the RT formula. That's if it's continuous interest. And then we had another growth formula that we use whenever it's compounded, say quarterly or some increment that you can measure. We had a different formula. But if it says the word continuous, which we're going to use a lot in section 4.6, it's this formula. So let me remind you the players in this formula. E is the original amount of your startup amount. If it's money, it's kind of easier to think of, I think. So how much you started in your investment, your principal. And A is the growth amount, what it grows to. E is this neat little exponential value that's on our calculator. The e to the x, exponential e, should be found on all your calculators. For example, I like to show you my calculator, and it's on scientific as well as graphing. It should be on any basic scientific calculator. Can you see on this one, it's this above in yellow, above the LN button. A lot of times those are together because they're related, as we've been seeing in the last section. So you have to hit the second function to get that there. Now, I think I've explained to you on this calculator, it's sort of a backwards calculator. If you're going to say e to the second power, say I try to hit the e button, it doesn't really work that way. I have to hit the exponents, then hit the e. So that would be e to the second. So if I wanted e to the first, regular e, what is the value of e? I would hit 1, make the exponent 1, and then do the e to the x button. So e is about 2.718, yada yada. Sort of like pi, pi has an irrational value that never terminates, it never repeats. Well, e is like that as well. It's just an application that shows up in our world. So this is e to the first power. And on this calculator, to get e to the first, where is that e? Here it is. And sometimes you have a regular e. Oh, let's see if you can see this. Let me get it a little closer. I have two e values. I have regular e. Do you see that over the divide sign? In yellow, I have a green and a yellow here, so you can do either. But I need the yellow. Let's see, did that work? Okay, so E equals. So just regular E equals. It has an E without an E to the X as an exponent, so I can just hit E. But most time when we're E, and you see the application here, we're doing E to some power. So we want this one. See the X, right? And all that does is just trying to help me with keystroke. It already has it as an exponent, an up arrow, and a parenthesis. So if I want to do E to the first, just regular E to the first, there's that 2.718 value that we talk. The calculator may have two E buttons or just the one, but it's not a biggie because you can definitely either way. All right, so that's what E is, and in this application, we're definitely raising it to an exponent, so E to the X is handy for us. And the exponent is the rate of interest, and then the time, the number of years. If it's a yearly interest rate, it should be time in years. These should correspond. All right. So in this one, we said find the doubling time of an investment at 6% interest, compounded continuous. It doesn't tell me how long or how much we start with or some of the things it told us in a previous section. But we can still solve this because it's just saying when will this p-value. It really doesn't matter if it's $1 or $1 million. The answer is the same. And you could test it out with some values because that might seem strange, but it's true. So it doesn't matter what p is. If p is $3,000 or $6,000 or $10 million, we're looking for that to double. So we're looking for A to be 2 of P, twice P. So that becomes our inputs. And then, the other thing they told us was the rate. I guess I should go ahead and write that in. So we want it to grow to twice P. We don't know what P is. And we want the rate to be 6%. So change that to the decimal point. 0.06. We always have to change our percents to decimals when we solve equations, unless otherwise noted. All right, so that's all I've got. So you might say, well, I've got too many unknowns. Your big unknown, we're trying to find time, find the doubling time. So we're trying to find t, that's our variable we're asked to find. And it looks like e is not a variable, remember? E is 2.718. So that's not a variable, but p is a variable. So I do have too many variables, but I can take care of that because since this is multiplied right there, I can divide by p on both sides, and p cancels out. So that takes care of that variable, and I have the equation 2 equals e to the 0.06 t. Now I've got something that's solvable, only one variable involved. This is basically what you'll do if it's tripling time, quadrupling time, 2.6 time, 75% time, whatever element of time, it'll be that. In this case, doubling, so it's 2. Again, if it's tripling, you'd have 3 equals e to the RT. So what I have to tell you is if you're doubling, tripling, if it's a deteriorating thing, it might be like a half-life or something. It'd be a half, but whatever increment you're going to get it equals e to the RT or ERT, say. So they do rate of growth or decay. All right, so how do we solve this? We need to get this exponent out of the exponent place down on the level I can work with it. And you might remember from the last chapter, what does that is a logarithm. We need to take the log of each side so the exponent will come down. So we have two types of logs, the common log, the LOG button, or the natural log, the LN log. Now, ln and e go together. We've talked about they play well together, you might say, and it simplifies easier. So I recommend you use the ln logs on these. So I'll take the ln, the natural log of each side. Now, this side is ln of 2, which we can type that on our calculator. It's a value on our calculator. This side, why we did this is so this exponent will come down as a multiplier. That's one of our log rules we learned in an earlier section. So now that is times in front of this ln e. And then you can find the ln of e on your calculator will be 1. Why is ln of e 1? Because ln means you have base e, a base e log. And e to what power is e, the meaning of a log? Well, that's 1. Or you can just check it on your calculator and see that it is so. ln of e is always 1. So that makes our equation even simpler. So we have ln of 2 equals 0.06 t. And then how do we solve that? We divide by what's with our variable. Divide by 0.06. And time will equal this off of our calculator. So let's type that in. ln of 2, don't forget to close that parenthesis, divided by 0.06 equals 11 point, and there's a decimal, and depends on what your problem says to round to. I forgot to see. But let's say it says round to the nearest 10th place. 10th is right after the decimal point, so that 5 tells us to round that up to a 6. So it's 11, 6, and that was in years. So, and this is just going to be true for any investment, like I said, no matter how big or small. If you're looking to double your investment at 6%, if you're getting 6% interest, that happen in a little under 12 years. It takes about 12 years to double your investment at 6%. All right, this example, number 2. Out-of-pocket health expenditures. This is a modeling, and it really does get to the root of a lot of the meaning of algebra. If you've kind of been questioning what's the meaning of this, modeling is a big meaning in algebra. We have different types of functions that we've studied throughout the class. We have exponential functions, log functions, parabolas, square root functions, linear, many types of functions and their behaviors you've been studying in this class. But what of that? What do you do with that? I know graphing's so much fun, and I really do think that's fun, but what of it? Why are we doing it? And it's so we can actually model real life problems, things that come up in businesses and healthcare and so on. So in this example, we see that. We've got a model. They said this is to model the out-of-pocket health expenditures from the years 2004 to 2009. Now that might not help us so much because we already know what happened in 2009 at the writing of this book, so it was kind of old information. But a lot of times we use models to predict what's going to happen, say in the year 2030 or something. So we use models to predict future values. So this one's kind of already past because it's older, but the idea is still there. That's how they do that. And then they say maybe x equals 0 is the year 2004. So this model started in 2004, x equals 0, so x equals 1 would represent 2005, and so on. So then it gives us this function. Again, this is where they modeled what the behavior of the graph was looking like to make their predictions, and said, question A, what should the expenditures be, the out-of-pocket expenditures in 2009? So we have to figure out how to infer what 2009 means in this model. So we can't plug in 2009 for x because it says it refers to smaller numbers. The year 2004 0, so 2005 is 1, 6 is 2, 7 is 3, 8 is 4. So 2009 is x5. It means plug in x equals 5 to this model. So we input 5 right there. It'll be y, or f of x, equals 2577, which we have on our calculator, 0.0359 times 5. Those are the inputs to our calculator. So how's that look? Y equals 2577. Do you have to put a time sign? I'm not sure. It depends on your calculator. I'm not even sure on this one. I don't think I do. So, oops, put the wrong thing even there. I need my e to the x next. E to the x raised to the 0.0359 times 5, close your parenthesis, and there we are. So I did not need a little time sign between these two. Your calculator may. Just depends on how it's programmed. But I get 3083.6869. Since we're talking about money, we always round to the nearest penny, which is the hundredths place. This 6 will round that up to a 7. So to the nearest dollar, and there we go, 69 cents. And that's what a person's out-of-pocket is projected in the year 2009. Well, I guess we could Google that and see if that really was a true deformed value. All right, next part, B part. It asks the other way. It says, what year was it 2878? I bet it was before then. I bet it was before 2009 because it went up to over 3,000 in 2009. So I could kind of estimate maybe it's going to be the year 2007 and maybe plug in those numbers and see if you want to kind of work backwards. But we can tackle this directly with our algebra. That is the y output, what we want y to equal over here in the answer part. So we put the 2878 as the what it's going to grow to, and then 2577 was the beginning part of this model in the year row, x equals 0, and then we can work backwards with our algebra magic to solve that, right? So how do we solve that? First of all, we will divide and simplify that a little bit by the 2, 5, and 7. Remember, those are times between there, so we're at liberty to divide out along to simplify. So that will get rid of that part and simplify our equation. Now let's see, if I punch that on my calculator, it's probably some awful decimal. And you know how we don't like awful decimals. We want to try to keep simplified. Okay, so it's a long decimal. And you know, if it would have been 1.32, some terminating decimal, that's okay. But with these long decimals, you'll have some round off error if you're not careful. So I keep that intact and just call it that. Division equals e to the rate times time. Then to solve for x, I need to bring this down on the level by taking the ln of each side. So we take the ln of each side. So we got the ln of this fraction going on equals this in front. This exponent is now down times ln of e. Just like on the last example, ln of e is 1. So you can knock that out. And then to solve for x, we divide both sides by what's with our variable, since that's the understood times between those. And then we divide on this side. And then we carefully type that in, our handy-dandy calculator, right? So we've got, oh, I shouldn't have erased that. I had that. ln of 2878 divided by 2577. And then take that answer divided by 0.0359 for an answer of x equals 3.077. So we could approximate that to x equals 3. I think we'll be close enough on that. I'll check and make sure about that. But x equals 3, what does that mean? X equals 0 is the year 2004. So 3 years later, that's the year 2007. So the ultimate answer there is in the year 2007, the expenditures got to that 2,878 per household.